So welcome back everyone to this session, which should hopefully finish chapter 2 and therefore module 1. Last time we were discussing empirical formulas. So empirical formulas were used for things such as compounds, like ionic compounds. So usually we're given some sort of percentage mass from which we are to calculate the empirical formula of a compound, like iron oxide, for example, which is what we'll do next, or sodium chloride, or magnesium oxide, things like those. So we're given some sort of percentage mass, so percentage of element A and percentage of element B, and then we're told to convert this into a mass. So usually percentages are base 100, right? So 70%, 30%, that type of thing. So we would then directly convert that into grams. So for example, if we have, as I said, 70 and 30 percentage of A and B, then, so it's percent, then we would convert that directly into 70 grams and 30 grams, like so. We would then use the molar masses of those to determine their number of moles. So we don't know what A and B are, so we can't do that step, but it would be 70 times 1 over whatever the molar mass is. And then we would use those number of moles to find out what the mole ratio is. So that would be moles of X over moles of Y. So it would be 1 of A to X of B. And then we would multiply B by whatever number would create a whole number. And then this would then give us a ratio of A to B. So we would have A to the A and B to the B, where this could be 2, could be 3, could be 1. It'll be an integer. So all elements should, all compositions that you're given should eventually lead to a whole number ratio of the element. If it doesn't, then there might have been a mistake somewhere along the way. So just check your working because in all empirical formulas, you will have a whole number to a whole number. Okay, so the example we did last time was this one. Magnetite is composed of only iron, Fe, and oxygen, O, and is 72.36% iron by mass. What is the empirical formula? So the first thing here to do is, as we did in the previous one, convert percent composition to mass, assuming a base 100 grams. So this case, iron is 72.36%. So we converted that to 72.36 grams. This then gives us oxygen as being 27.64, whatever is remaining in the percentage, because remember, magnetite is only iron and oxygen. So here we have the masses of iron and oxygen. Then we would convert these to moles. We get about 1.29 moles of iron to 1.71 moles of oxygen. We just use the mole or mass to mole conversion that we learned about previously, which is the mass times 1 over the formula weight of iron. Gives us this, so it would be 72.36 times 1 over 56 would give us the moles of iron, and then we would do a similar calculation for oxygen, where it is 27.64 grams times 1 over 16 to give us this many moles. We then simplify the mole ratio, so we have moles of X over moles of Y. So if it is iron over oxygen, we end up with 0.75 iron to 1 oxygen, or if it's oxygen over iron, we have 1.33 oxygen to 1 iron. So this is to the base 3 and this is to the base 4. So if it's this ratio we're using, we'll have to multiply by 4. And if it's this ratio we're using, we have to multiply by 3. Both are perfectly fine. So the answer using this one, the answer in your textbook will be this. So it will be 1 mole to 1.33. So we multiply this by 3. So we get 1 mole of iron becomes 3 moles of iron. So it becomes Fe3. And then 1.33 moles of oxygen becomes 4 moles of oxygen. The other way around then is 0.75 moles of iron to 1 mole of oxygen. So we have to multiply this by 4. So we get 0.75 times 4 is 3 moles of iron. So Fe3 to O4. 1 times 4 is 4. And so that's how we would do the empirical formulas for an example like this. So then there is another way of, if we want to calculate a formula from a percent composition. So here you're using strategy map 2.9 from your textbook. So the problem is to determine the empirical and molecular formulas based on known composition and known molar mass. So we have the molar mass of the compound. So this is the total mass of the molar composition. Then we have the percent composition. So assume each atom percent is equivalent to mass in grams in the 100-gram sample. So that's the same as what we did with the empirical formulas. So 70% in the molar mass is 70 grams. Mass of each element in 100-gram sample of the compound is then determined. Step 2 is to use the atomic weight of each element to calculate the amount of each element in the 100-gram sample. So multiply mass by moles over grams. So the amount of moles of each element in the 100-gram sample is then determined. So we then divide the amount of each element by the amount of the element present in the least amount. So whichever is the lowest abundance in the composition. So the whole number ratio of the amount of each element to the amount of element present in the least amount is equal to the empirical formula. And then we can divide the known molar mass by the empirical formula mass to get the molecular formula. So this is a little bit more involved than the empirical formula. It has one more step, but don't worry about that. We're going to show a nice little example. So let's do the practice. So this example that we're going to be looking at today is this hexamethylene diamine, and it's one of the materials used to produce a type of nylon. So elemental analysis gives us 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. So this all adds up to 100. And we're being asked what is the empirical formula? And then after we've determined the empirical formula, we can use the molecular weight, which is 116 grams per mole, to determine the molecular formula. So the first step, as always, is to convert these percentages into masses. So we'll determine X, Y, and Z in CH₂O. Because remember, we know that there's carbon, hydrogen, oxygen because we were given the sample composition of carbon, oxygen, hydrogen. These numbers multiply or add together to give 100%. So we know that it only contains carbon, oxygen, and hydrogen. So since the percentages for each element sum to 100%, if one equates percentage to grams, the sum of the masses must be 100 grams. So we can assume 100 grams of the compound. This just makes our calculations easier. So we will have 64.82 grams of carbon, 21.59 grams of oxygen, and 13.59 grams of hydrogen. The next thing is to convert the grams of each element to moles. So grams of the element X to moles of element X, for example. So for carbon, we have 64.82 grams of carbon times 1 mole over the molar mass of carbon, which is 1 mole carbon divided by 12.011 grams of carbon, which gives us 5.397 grams or moles of carbon. And then oxygen in a compound is always monatomic. It's not a diatomic here. So it's 21.59 grams of oxygen is times 1 mole of oxygen over 16.00 grams oxygen, which is equal to 1.349 moles of oxygen. And then the same applies to hydrogen. We only have hydrogen as a single atom, monatomic. So that's 13.59 grams of hydrogen times 1 mole of hydrogen over 1.0079 grams of hydrogen will give us 13.48 moles of hydrogen. So we now have the numbers of moles, and the one that's present in the least amount is oxygen, and so we'll be using that later. Divide each of the individual moles by the smallest number of moles to gain the molar ratios for each element in the compound. So here we have 5.397 moles of carbon, 1.349 moles of oxygen, and 13.48 moles of hydrogen. And so these are for the formula subscripts, so CX, HY, OZ, etc. So the subscript for carbon is going to be 4.001, so it's 5.397 divided by 1.349. 1.349 is the moles of oxygen, which is the one that's present in the least amount because it's the smallest number. Then we do the same for hydrogen, which is here, which gives us a value of 9.992. And then for oxygen, which gives us a value conveniently of 1. So that means the ratios, if the ratios are fractional, 0.5, 1.5, or 0.333, multiply each ratio by a whole number to get an even number for the formula subscripts. So for example, if it's to the base 0.5, then it's times 2. If it's 0.25, it's times 4. If it's 0.333, it's times 3. So this is similar to what we did with the iron oxide magnetite question earlier. So rounding to the nearest whole numbers, we have, because remember you can't have 0.001 carbon or 0.992 hydrogens. So we round to the nearest whole numbers because remember, some of the discrepancies between the whole numbers is caused by our rounding and the way that we carry numbers forward. So we get the empirical formula here as C4H10O. And so the result of this calculation tells us only about the empirical formula of the compound, not the molecular formula that we want. So we've answered the first part of the question, but we still need to answer the second part. So determining the molecular formula. So for some compounds, the molecular formula is a multiple of the empirical formula. The empirical formula is here, and the molecular formula is here. So the empirical formula is multiplied by some value n, which is also equal to the multiplication factor of the subscripts here. So n is equal to 2, 3, 4, etc. It's always got to be an integer. So then we determine the molecular formula by looking at the empirical formula mass and the molecular formula mass. So if we remember back, we were told that the molar formula mass is 116. So we would divide the empirical formula mass by that number. So since the molecular formula is a multiple and is scaled by a factor of n, the molecular and empirical molar masses must also be scaled by the same ratio. So the empirical formula weight for C4H10O is 74.12 grams per mole. In a separate experiment, the molar mass of the compound was determined to be 222.1 grams per mole. So what is the molecular formula? So we would divide this number by this number. So 222.1 grams per mole divided by 74.12 grams per mole is equal to 2.996 or 3 to the nearest integer. And so this is going to be our value here. So the molecular formula for the compound is C12H30O3. And so that's how we would determine the molecular compound from the empirical formula and how the empirical formula can be determined from the percent composition. Hydrates then, we saw this earlier whenever we were talking about moles, we saw the copper chloride dihydrate. And so this is indicated by this little dot here. We have the salt, which was copper chloride earlier, and then there were two waters, so that was dihydrate. So these waters here are called waters of crystallization or hydrating waters, so they're called hydrates in the name. So a hydrate is a substance composed of an inorganic salt and physically bound water. So the water is not chemically bound here, so it can be removed, but it's usually present just as a stabilization factor or because the salt absorbed the water from the atmosphere. So N is the ratio of moles of water to 1 mole of salt. So N is equal to moles of water over the moles of MX, which is the salt. Naming hydrates is the salt name plus the prefix hydrate. So the prefix here can be mono, di, tri, etc. So we have barium chloride here, BaCl2, and then we have this dot, this middle or center dot. This indicates that we have bound water, physically bound water, which means that we have hydrating water, which means that we have hydrate. There are two of them, so that's dihydrate. So we would have barium chloride dihydrate. Here we have sodium sulfate pentahydrate. So sodium, so we have sodium here, and then we have sulfate, SO4 2-, so we have 2 sodiums. And then we have pentahydrate, so penta is 5. So here we have pentahydrate. Heating hydrate. So whenever a hydrate is heated, the water is liberated because remember, it's not actually chemically bonded together with the barium chloride in this state. So what happens is with heating, you can liberate that water. So you can evaporate away the water, which would leave a dry solid. So this is kind of a form of desiccation, removal of water. And so this then has the effect of liberating some steam or some water vapor. So for every 1 mole of hydrate, N moles, in this case 2 of water are liberated. After heating, any mass that remains is due to the salt residue. Therefore, any mass loss in heating is due to the water loss. We're not losing the salt here. The salt will not evaporate. Mass sample minus mass residue is equal to the mass of water lost. So determining the formula of a hydrated compound. So we're looking here to use strategy map 2.11. So we'll determine the formula of the hydrated salt based on masses of water and dehydrated salt. We'll then look at the mass of the sample before and after heating to dehydrate. Then we'll be finding the masses of salt and water by difference. The mass of salt and water in a sample of the hydrated compound will then be found. The next step is to use the molar mass of salt and water to calculate the amount of each in sample. So here we have multiply mass by the moles over grams. And so the amount of moles of salt and water in sample. And so we'll then, the next step will be to divide the amount of water by the amount of the dehydrated salt. And this will then give us the formula or the ratio of the amount of water to the amount of salt in dehydrated sample. And so let's do an example of that. So here we have, from the mass of the water lost, one can find the moles of water associated with the hydrate. So here we have barium chloride, here we have some water, and here we have the heating, which will liberate the water vapor, and then we'll be left with the salt, the anhydrous salt. So knowing the mass and the chemical identity of the anhydrous salt, one can determine the moles of the anhydrous salt. So the ratio of moles of water to moles of salt, N, is found by this equation here, where N is equal to the moles of water from hydrate over the moles of the anhydrous salt. Okay, so the next thing is to calculate the percentage of nitrogen in nitrogen trioxide, N2O3, where the atomic weights in atomic mass units are N is equal to 14.01 and oxygen is equal to 16.00. Okay, so 5 or 10 seconds to answer this, and then we'll have a look and see if we can't come up with the answer. You can pause at any time to get more times to calculate this one out. Okay, pause if you need more time. Answers coming soon. All right, so in this question, what we want to be looking at is we're calculating the percentage of nitrogen. So we're not given any masses or anything, but we are given the atomic weights, which is probably what we need to use. Not always, but usually. So here we're looking to find nitrogen content. So over the N2O3. So we want to find out how much nitrogen there is in this compound. So what we're looking at here is going to be the total mass of nitrogen, which will be from our sample here is going to be 2 nitrogens. So we'll have 2 times 14.01 all over 2 times 14.01. So this is from the actual dinitrogen trioxide plus 3 times 16. And so that will give us some fraction, which will be about 0.3686. And so we then multiply that by 100%. And that will then give us this answer here, 36.86. Okay. Then the next question is nickel silver, once called German silver, is the name for various silver white alloys of copper, zinc, and nickel, which do not contain any silver. A 35.452 gram sample of nickel silver contained 12.5% nickel. What was the mass of nickel in this sample? Okay, so please take 5 or 10 seconds to answer this one, or pause if you need more time. You probably will need to pause these. So have a think and pause if you need to. Okay, so it's really quite a straightforward problem. So what we're being asked to do is find the percentage or find the mass of nickel whenever we already know the total mass and the percentage of that which is nickel. So it's really just 35.452 times 12.5%. So that would, whenever we do this calculation, we would find out that the answer is this one, 4.43 grams. There you go, 4.43 grams. All right, so the next question is ammonium perchlorate. This is ammonium perchlorate. This is the ammonium part. This is the perchlorate part. Is a common fuel component of solid fuel rockets. If 75% of the oxygen in ammonium perchlorate was converted to molecular oxygen, how many grams of molecular oxygen would be produced from 117.5 kilograms of ammonium perchlorate? Atomic weights in atomic mass units are nitrogen 14.01, chlorine 35.45, oxygen 16.00, and hydrogen 1.008. So if you're given the atomic weights in the question, those are the ones you're supposed to use, not ones from a periodic table or anything like that. You're supposed to use the ones in the question if you're given them. Remember that this is molecular oxygen, not atomic oxygen. What is molecular oxygen? Keep that in mind. It's actually O2. All right, so 10 or 15 seconds, pause if you need more time. Again, you probably will need more time. Okay, pause if you need more time. We're going to answer this very soon. So the first thing to do here is to calculate the molecular mass of ammonium perchlorate. So we'll add 1 nitrogen to 4 hydrogens to 1 chlorine and 4 oxygens. And that conveniently gives us a value of 107.5 Dalton, which is the same conveniently as the mass. So the mass here is in kilograms. Remember that this would be 1 mole in grams. So if we have 117.5 grams of ammonium perchlorate, we would have 1 mole. Here we have 1,000 times that. So we have 1,000 moles of ammonium perchlorate. You can convert this to grams, this weight to grams, and then divide that by 117.5, and you will find that we have 1,000 moles of ammonium perchlorate. So from those 1,000 moles, we can produce 2 moles of molecular oxygen. Remember, molecular oxygen is O2. So there are 4 oxygens in every mole of ammonium perchlorate. So that means we could form 2 molecular oxygens, because 4 divided by 2 is 2. So we can form 2 molecular oxygens for every ammonium perchlorate we have. So 75% of that is then converted into molecular oxygen. So if we have 2 moles of oxygen for every ammonium perchlorate, that means we have 2,000 moles of oxygen in our 117.5 kilos. So we have 2,000 moles of oxygen, moles O2, and then 75% of that is 1,500 moles. 1,500 moles. O2, which becomes molecular oxygen. Then we times 1,500 by 32 grams, which is 1 mole of oxygen over 1 mol, which will be equal to 48,000 grams, which is 4.8 times 10 or times 10 to the 4 grams of oxygen. So we have this many grams O2. So our answer is this one. Okay. So then nitrogen and oxygen in the next question form a series of oxides with the general formula NXOY. One of them has 46.67% nitrogen. The empirical formula for this oxide is going to be what? I'll give you 5 or 10 seconds here to come up with the answer. Pause if you need more time. Pause if you need more time. I'm going to answer very soon. Okay, so this is a question that's very similar to what we've had before. We are not doing anything particularly new here. So we have 46.67% nitrogen. So that is equivalent to 46.67 grams of nitrogen, which means we're also going to have what, 53.33 grams of oxygen. Okay, so we then find out the number of moles here. So we multiply both sides by the 1 over the atomic mass of nitrogen and oxygen. So nitrogen is about 14 and oxygen is about 16. So multiply that by 1 16 and multiply this by 1 over 14. Okay, so we then find out that we have about 3.33 moles of nitrogen and about 3.33 moles of oxygen, nitrogen. So the molar ratio here is going to be 1 to 1. So we have NO as our empirical formula, this one. Okay. There we go. So the next one is the formula of the hydrocarbon decane is C10H22. The empirical formula is going to be what? 5 or 10 seconds here to answer this. Pause if you need more time, although you might be able to get this pretty quickly. Okay, pause if you need more time. Answer coming soon. Alrighty, so here, this is the molecular formula. So we want the empirical formula, which is the simplest version of this, and which still represents the same ratio of carbon to hydrogen. So CH₂ is not going to be it, because if we have 10 carbons, we should have 20 hydrogens, but we have 22. If we have C2H4, that would be times 5, so that would give us again C10H20. C5H11 is, because we multiply this by 2, we get C10H22, and C10H22 is the molecular formula. This is not the simplest formula. So our answer here is C5H11. Okay. Then the next question is the simplest carbohydrate in glyceraldehyde. Our simplest carbohydrate is glyceraldehyde, sorry. Its empirical formula is CH₂O, and its molar mass is 90.08 grams per mole. The molecular formula will be what? So take a moment to think about this, and we're going to be using some of the techniques that we've learned in this session. Okay, pause if you need more time, otherwise we'll be carrying on very soon. Answer coming soon. All right, so the first thing to do is find out what the mass of this is, the empirical formula. So the mass of the empirical formula is 12 from carbon plus 2 times 1 for hydrogen plus 16 from oxygen, which is equal to 30. So then we do 90.08 divided by 30, and we get a value that is around about 3. So then we multiply the empirical formula by 3, and we get C3H6O3 as our answer. There we go. So the next one is all of the following statements regarding 57.1 grams of octane, C8H18 are true except for which one? Take a moment to read them, and then 5 or 10 seconds for the answers, and pause if you need more time. You can always take more time. Okay, so we're going to answer it very soon. Answer coming soon. All right, so the first thing we probably want to do is find out what the molecular mass of octane is. So that's going to be 8 times 12 plus 18 times 1, which is going to be equal to, so 8 times 12 is 96 plus 18 is going to be 114, more or less. Then that means that 57.1 grams is probably going to be 0.500 moles of octane, so that one's okay. The compound is 84.1% carbon by weight, so let's see, so that's going to be 96 over 114. That's going to be equal to what? 96 divided by 114 is what number? Let me get my calculator. 96 divided by 114 is 84.2. So that's close enough. Okay. The empirical formula of the compound is C4H9. So C4H9, yeah, because if you simplify that anymore, you're going to get a non-integer value. So that seems okay. So that means that this one must be the incorrect one. And we can check that by looking at the molar ratio that exists here. So what we have here is we're going to have to think about what percentage of octane is actually hydrogen. So earlier we had 84.1% is carbon. So that means that 15.9% is hydrogen. So 15.9% is hydrogen. So that means that we're going to have 57.1 times 15.9%. So if it's 15.9% hydrogen by weight, we can determine that the 57.1 times 15.9 is going to be about 9 grams of around about 9 grams hydrogen. So this one is incorrect. And that's true. All right, join in number 41. A hydrocarbon has the empirical formula CH₂. If its molar mass is 140.3 grams per mole, what is its molecular formula? Again, 10, 15 seconds. Pause if you need more time. All righty, so as usual, pause if you need more time. The answer's coming soon. Right. So whenever we're converting between molecular formulas and empirical formulas, what we usually do is the first thing is to find out what the mass of this empirical formula is. So carbon is 12 plus 1 for hydrogen times 2, because there are 2 hydrogens, is equal to 14. So 140, which is the mass of the or 140.3, which is the mass of the hydrocarbon, times 1/14, which is the mass of our empirical unit, will give us about 10, thereabouts. So that means that this is our answer here. Because CH2 times 10 is C10H20. Okay, join in number 42. You combine 6.54 grams of zinc with oxygen and find a white powder, zinc X, oxygen Y, with a mass of 8.14 grams. The empirical formula of the product is what? Is it ZNO, ZN2O, ZNO2, ZN2O3? Take a moment to determine your answers, and then we'll go through the answers. Pause if you need more time. Okay, answer coming soon. Pause if you need more time. All right, so the answer is going to be determined by first finding the composition of this, which is of this final mass, which is zinc. So zinc has a mass of 65.4. Oxygen is 16, as we know from before. So what percentage of this is this? So 6.54 divided by 8.14 is equal to, or as a percentage, times 100% is going to be 80.3%. So the remaining 19.7% is oxygen. So that's going to be 19.7 grams of oxygen, which is equal to how many moles? 19.7 divided by 16, 1.23 moles. 1.23 moles. Okay. Okay. So then the 80.3 grams of what's this, of zinc is, so this one is going to be 80.3 grams of zinc, which is equal to so 80.3 grams of zinc times 1 over 65.4, which is this one, will give us 1.23 moles of zinc. So the mole ratio here is 1.23 to 1.23, which is 1 to 1. So that means we're going to have this as our answer here. All right, the last question. So a compound of sodium and oxygen has 58.96% or sodium and a molar mass of 77.98 grams per mole. What is the molecular formula of the compound? Is it Na2O, NaO, NaO2, Na2O2, Na2O3? Take a moment to determine your answers, 10 or 15 seconds, pause if you need more time, and then we'll go through the answer. Okay, pause if you need more time. Answer coming soon. Alrighty, so what we've got here is sodium and oxygen. So it's 58.96% sodium, which has an RAM of 23 Dalton. Oxygen is of course 16 Dalton. So then if it's 58.96% sodium, we have 58.96 grams sodium, which is how many moles? So it's 1 over 23 is equal to, get my calculator, 2.56 moles. All right. Then if we have that, so then we have the rest is going to be what, 56.96%. So is 40, so it's going to be 41.04 grams oxygen, which is how many moles? 1 over 16 is going to be equal to 2.56 or thereabouts moles of oxygen, moles of sodium. So that means our empirical formula is going to be NaO, because the molar ratio here is 1 to 1. So NaO has what is the mass of NaO? Because now that we've got the empirical formula, which is this, we still need to, but the molar mass is this. So is this molar mass the same as the empirical formula mass, or is it different? So it's going to be 23 plus 16 gives us a formula mass or an empirical mass of this one of 39 Daltons. This is not the same as 77.98. So then we need to find out 77.98 times 1 over 39, which is the mass of the, that's a 39, not a 9 or whatever, is equal to 77.98 divided by, or times 1 over 39 is equal to 1.99, which is approximately 2, which is around about 2. So that means our formula is going to be Na2O2. It's going to be this one, which is the correct answer. So it was the last question of this module. We'll be doing a quiz soon. as is usual after the end of the module. Thank you for watching this, and please enjoy reviewing it, and hopefully we'll see you in the next session, which will start module number 2. Bye-bye.